Hopefully we'll have more chairs next time. So that's number one. Okay, and now let's get started. So the first person who's going to be talking today is Fred, and he's going to be talking about the 5 stages of enterprise Jupyter deployment. And he's going to go for the first hour, and then we have another talk afterwards, which is on Airflow, 2 years in production. So let's give an introduction to Fred. Yes, please use the mic. We are going to be recording. Chester, you agree with that? We are recording.
Okay, yeah, already started. All right, thank you for the introduction. Let me get the slides going. Let me get the slides going.
It's opposite. One moment, please. We are experiencing technical difficulties. Did you do that before? No, I really didn't.
And now you've all seen my second
Okay.
slide.
No.
So the suspense has gone away. So here's that second slide again. Hi, I'm Fred. I work down the street at 505 Howard Street.
Your mic's not working, by the way. Sorry on that.
The mic is, I think, not for you. No offense, but it's for the people who are watching the live stream. So in this room, I'm just going to have to project. Is this level of loudness okay for everyone in the back? We're good? Okay. So if I start getting too quiet, just let me know. I'm Fred. I work for IBM. I work at 505 Howard Street down the road at the IBM Watson West building in a open source lab called CodeDate. That stands for Center for Open Source Data and AI Technologies. We work on the foundational open source projects behind the analytics in IBM's portfolio. I've worked at CodeDate since the beginning of this year. Prior to that, I had the same title, same organization, but we had a different name. We used to be known as the Spark Technology Center. Before there was a Spark Technology Center, I worked for IBM Research for about 9 years, and that was my first job. So enough about me. You're all here to talk about Jupyter, and it's so exciting to see so many people come out to talk about DevOps. Really great. So how many people here know what is Jupyter, or familiar with Jupyter? Oh, that's very good. So like 95% of the people in the room know. For the remaining 5%, I'm going to give a quick introduction, and the rest of you, by the time this is done, you'll know a whole lot more about Jupyter. So Jupyter in a nutshell is a project that has been around for quite some time. It actually started, well, Jupyter started in 2014, but the history of the project goes way further back to something called IPython. IPython was a project to create a better interactive console for the Python language. Python comes with a built-in console, but it's not terribly good. It's mostly for emergencies. IPython added a console with better scroll back, multi-line commands, and importantly, the ability to open up a window and display graphics. This became quite popular, and then the web came around, and IPython added something called notebooks. This is the same console, same software on the back end, but the front end is in a web browser. And when everything's in the web browser, your text and your graphics can all be inline, and you get an experience kind of like a scientific notebook with your equations and your graphs all in a nice place. This became very popular and eventually grew into what is called the Jupyter project. When Jupyter notebooks today extend far beyond just Python and just these simple graphics, but the same terminology still applies. So here's a brief overview of that. Notebooks are made up of cells. Each cell consists of a command, user input, and a response, what the system sent back. What the system sends back could be text, it could be graphics, it could be tables, it could be quite a few other things, and we'll get into a few of those other things later on. But it's the recording of this conversation between the user and the system. Jupyter notebooks usually operate, when a data scientist uses Jupyter notebooks, they'll typically connect to this client-server architecture. The server may be on your laptop, or it may be remote. The server stirs up the notebooks, and the server behind the scenes is running all the interpreter processes that run the commands. And it's common for a data scientist to open up many different browser tabs, to have multiple notebooks open, maybe your old experiments, your new experiments, your data analysis all at the same time. the Jupyter project noted that this was happening, and they created a new front-end UI called Jupyter Lab that looks a lot like an integrated development environment. But the key thing to note for the purposes of this talk is that this interface and the interface on the previous slide and the IPython interface and even that text interface, they all have the same infrastructure behind the scenes. So to summarize, Jupyter Notebooks are a fairly old technology that has stuck around because it's so very useful for doing data science and also for doing science, physical sciences, social sciences, computer science. All of those scientific endeavors go through many steps that are greatly helped by having notebooks, ranging from analyzing your data, constructing experiments, looking at the output of your experiments, presenting that output of the experiments. Notebooks help you to do all these things by collecting your interactions with the computer in a form that you can easily share. I should also note that Jupyter is a big part of our IBM Analytics product line, particularly in IBM Watson Studio. That's our premier machine learning environment. So enough about Jupyter. Today's talk is about Jupyter in the enterprise, and in particular, the process that we in CodeDate have gone through and have seen others go through in deploying Jupyter into the enterprise. So how many people here work with enterprise software or on enterprise software? Okay, a lot fewer. So I'll go a little slower here than the Jupyter parts, because we need to say, what is enterprise software? And to answer that question, you need to say, what is an enterprise? An enterprise can be a business, an enterprise can be a nonprofit, an enterprise could even be a government agency like NASA. The key thing that defines what is an enterprise, it's an organization that has a combination of scale and focus. An enterprise focuses on a relatively small number of problems for its size and puts economies of scale to work at solving those problems, whether it's the United Way trying to solve world hunger, or IBM trying to solve the problem of building software for enterprises. You work at large scale to focus on solving those problems. As a result of working at scale, when you look at how software works in the enterprise, there are certain requirements that come into play for any kind of, in this case, analytics software, regardless of what it is, and in particular for the Jupyter stack when you want to run that in the enterprise. Enterprises, when they do data science, typically do data science with large teams of data scientists because they're focusing on large problems. They often have large amounts of data to crunch through to solve those problems, hence the large teams. So you need to support collaboration among all these users who are working together. They need to collaborate when working with very large-scale data, either by going onto the cloud using Kubernetes to get some big machines, or by spreading that data across multiple machines with a system like Spark. All this needs to work with the notebooks. In addition, since you have all these people working together, you need some way to manage all these people, hence additional requirements come into play for security, authentication, auditing, data access control, because that data is very valuable. So these are very common things if you work, as I have, in the enterprise software realm. And I have to be honest, when I first thought about, or was presented with the problem of adapting the Jupyter open source stack to all these requirements, my initial reaction was, so what? Because notebooks, if you look at them at a high level, are just really about shipping strings around. The user types in a string of code in a cell. The JavaScript picks up that string, passes it on to a server. The server passes the string on to a Python subprocess. The subprocess executes the string as code, gets the result back as a string, it goes back up through the stack, and the result appears in the window, right? So if you want to layer some enterprise functionality on top of this, conceptually at least, all you have to do is take this server layer and replace it with something that still passes strings back and forth, but also has some additional enterprise-y functionality. So I reached this point very early in my exposure to Jupyter. A lot of other enterprise architects also reached this point, and I like to call this point the first of 5 stages of a Jupyter enterprise deployment, enterprise Jupyter deployment. In particular, I call this phase denial. So, denial because it's actually not quite so simple. Remember that simple client-server diagram a couple slides back? Well, actually, Jupyter needs to do quite a bit more besides just pass strings around, and as a result of that, you end up with an architecture that's considerably more complex. So in particular, the things that Jupyter has to do to really bring that ease of use that's made it so popular is, number one, it's not just executing one string after another. You can queue up multiple cells for execution in Jupyter, watch them executing in real time in the background as the results stream back. You can interrupt or cancel that execution. You can spawn off a background process and watch it put stuff at the top of your notebook while other things are happening down further below in your notebook. So you have much more control than you might think, and there's a lot of complexity behind the scenes to make that control happen. Also, the thing that comes back from Jupyter is a lot more than just text. There's a lot of support for rich media types. There it is. A lot of support for many types of rich media. And also you can do some things you wouldn't expect to be able to do. You can start a profiler inside your notebook. If some of your analytics code is running a little slow, you can open up a debugger, drop into a debugger if something crashes. These are two examples of things that Jupyter calls magics, which are extensions to the notebook framework. If you go into the manual for Jupyter, you'll find 90 magic commands built in. If you look online, you'll find over 100 on the IPython repository and dozens of other ones spread over the internet at various other open source repositories. So there are many, many extensions to Jupyter, and they all work to add rich functionality to the notebook. For example, this is an extension called Pixie Dust that gives you the ability to do interactive visualization of data inside your notebook without writing any code. If you want to write a little bit of code and get even cooler visualizations, there's another library called Brunel that lets you do a whole other class of visualizations of your data, again, in the notebook with a little bit of code to configure it. And so these are both magics for Jupyter. So this is the kind of thing you get with magics. And as a result of all this complexity, all this functionality rather, there is quite a bit of complexity on the back end. This is what the architecture actually looks like, where each box represents a major chunk of the Jupyter code base. Okay, so strings come in, but a whole lot of other stuff that happens in the middle. And we'll go into this in just a moment. But the key thing to realize is that this is complex. And when you start delving into some complexity and some of the choices that have been made in building this architecture, that is when you reach the second phase of enterprise Jupyter deployment, which is anger. Anger because this was not designed to be used in the enterprise. A couple things to point out here. Number one, all this stuff on the right in blue, that's all designed so it's to run on a single machine. Keep that in mind as we move forward. This all needs to run on a single machine, and every kernel, every window that you have open in your environment as a data scientist has a separate kernel and so a separate process. And all these processes have to run on the same machine. And in between that Python process and the rest of the stack, you have not just passing strings back and forth, but actually 5 asynchronous message queues. So you can do things like queuing up commands, interrupting a sequence of commands, streaming results back, and stuff like that, or killing a non-responsive kernel, for example. You also have a number of third-party kernels. The IPython kernel was the first, it's the most common, but there is a very long tail of over 100 different other kernels you can use if you want to, say, run R in Jupyter, if you want to run Scala, if you want to run Python with some additional elements in your environment. There's custom kernels that people have to run, so you can't just swap out the kernel with something enterprisey. In addition, if you want to have multiple users collaborate in a notebook environment, like we do with Watson Studio, where people can send notebooks back and forth and version their notebooks and share them online, well, all the collaboration facilities in the Jupyter stack are in that notebook server, which, remember, has to be on the same machine as all the kernels. So this machine in your mind should be getting very, very large. And it gets even larger because your Spark driver needs to be on the same machine too if you're using Spark. If you're running TensorFlow, all your TensorFlow computation has to happen on the same machine. And if the first user to get to the GPU gets the GPU. So this is not really a good environment for doing multi-tenancy and security and all those other enterprise requirements. So lots of challenges that you have to overcome, which can make you a little bit angry, as I said. So when struck with this, the typical reaction that an architect will have is to stand back and say, maybe all those enterprise requirements aren't quite so important. Maybe we can dial back the requirements a bit. I like to call this phase bargaining. So we're going to say, okay, these requirements are expensive to meet. We still want notebooks. Let's see if we can come up with a cheaper solution that's good enough. So I'm going to go through 3 different types of solution, which may be good enough for your organization. If they are good enough, then go ahead and use them, and I've got some links to how you can deploy them. For IBM, these were not good enough. So anyhow, on to compromise number 1. Have a gigantic server. You notice while I was going through that presentation a couple of slides back, the server was getting larger and larger and larger in your mind. In some cases, if you have a relatively small team and relatively small data, maybe you can fit everyone into a single server and run the whole Jupyter stack on that machine. Then everyone is able to collaborate, everyone is able to run all their kernels. The issues that you get with this compromise should be pretty obvious. That machine needs to be big enough, and you very quickly reach a state where no machine is big enough if you're talking about big data and big teams. And also, all those people need to be logged into the same machine, and that may not be in line with your security policies if you have to enforce some separation between subteams. So another compromise that you could use, in this case, which requires some additional software, is to have a separate instance of that whole Jupyter stack for each user. You stick a proxy server in front of the whole architecture, and then each user gets their own entire notebook stack. This gets you better scalability in terms of users, since every user gets to run on their own machine, or these days usually on their own Kubernetes pod. But you haven't solved the problem of scalability with respect to your data, because when the pod with the user's Jupyter stack starts up, at that point the size of that pod is fixed. And depending on what the user does, chances are that pod's going to be either too big, which wastes resources, or too small, which crashes kernels. The other thing to note is all the collaboration features in Jupyter Notebooks and any extensions to those aren't going to work because everyone's on a disjoint stack. And you also have an entire proxy layer to deal with. Which brings me to a third option here. Oh, by the way, there is a project called Jupyter Hub, which you can find online, that implements this approach. Again, if you have an organization where these compromises are acceptable. The third compromise that you can do is to replace that kernel. If you know that everyone is always using the IPython kernel, you don't care about the IR kernel, you don't care about Scala and things like that, then you can take that kernel and swap it out for something more enterprise friendly. Maybe a proxy that talks to a RESTful web service. There is a system called Apache Libby that implements this approach. We actually OEM Apache Libby through our relationship with Hortonworks. We have a committer in my lab on Apache Libby. So we like Libby, but it is a compromised solution. In particular, since you have gotten rid of the IPython kernel, you've gotten rid of the IPython kernel's extensions. You've gotten rid of all those hundreds of magics. You've gotten rid of most of the data visualization capabilities. You can't use other languages unless your system implements this entire thing for other languages. And also, unless you are really, really clever about this proxying, you will break your ability to interrupt things freely or kill unresponsive kernels. So we considered all these options in IBM and got through the bargaining phase. And that led to phase 4, which is depression. So if you get to this phase, the rest of this talk is how we can get past that depression and on to phase 5, which we call Jupyter Enterprise Gateway. And that's the project I'm going to be pitching you tonight. The story behind Jupyter Enterprise Gateway involves 2 different product groups that simultaneously were working through these 5 different stages and had reached roughly the depression phase. We had implemented all a combination of all three of the compromises I just talked about. It looked something like this. We had a Yarn cluster. We wanted to support notebooks on Spark on Yarn. So what we did was, like in the big server mode, we took all the notebook code and we ran a single notebook stack. To get back some of that multi-user collaboration functionality, what we did was we took what was called the data science experience, and today is known as Watson Studio, and we would run that to manage the notebooks themselves, but then we would proxy just the notebook layer, the kernel layer of Jupyter down into this notebook node where we have a system called Jupyter Kernel Gateway managing that layer. And we also could support open source Jupyter stacks too as the client. So this looked okay until we started seeing what it can and can't do, and two very important limitations came about here. While we had gotten back some of that multi-user functionality by having a multi-user front end and a proxy, we still had all of these all these kernels are running on a single node, and because of the way that Spark and Jupyter interacted, all our Spark drivers are running on a single node, and that gets to be problematic because a Spark driver is a very big, heavy-duty piece of machinery. The second issue is that in the process of doing all this integration, we managed to pretty much break Spark on Yarn's security model. So all of these Spark jobs will run as the same user. So effectively, you need to have all your users be really good friends in order for this to be a functional solution. So we had a prototype that worked like this. It was determined that it wasn't good enough for enterprise use, so we went back to the drawing board. And we focused primarily on that issue number one, which is that all the kernels are running on a single node, because that was the real deal killer here. When you have teams that get larger and smaller, you want to be able to scale up your Yarn cluster to scale up the size of your team. Each user is going to have some budget of kernels that they can run. And if you look at the number of simultaneous kernels you can run, on the x-axis we have the number of nodes in your cluster. On the y-axis you have the total number of kernels you can run. With this architecture and 4 GB heaps on your Spark drivers and a 4-node cluster, we can run 8 kernels because there's only one node that runs kernels. And with an 8-node cluster we can run 8 kernels. And with a 12-node cluster we can run 8 kernels. So this is not so good for scaling up your team. So this was the real deal killer. The security stuff was sort of icing on the cake or gasoline on the fire, I guess you could say, that made this extra non-workable. So, and this is an extra big problem because in a typical Jupyter session and a Jupyter Lab session especially, you'll have lots and lots of kernels open. So our initial goals here were we were going to go back to the drawing board and buckle down and do all the hard work to make this really work in the enterprise. And we're going to optimize our resource allocation so we can scale up not only in terms of users, but in terms of data. We're going to have proper multi-user support and enable Spark's on Yarn's impersonation capabilities. And we're going to secure all of the unsecured connections that are present in normal Jupyter's notebooks. All those message queues, by the way, are on unencrypted TCP sockets by default. This is what we came up with. It's called Jupyter Enterprise Gateway. And it looks kind of similar to the original prototype with some significant differences. So as before, we can have a multi-tenant notebook environment that many users can connect through there and share notebooks. And the bottom layer of that notebook stack, the one that runs kernels, is proxied into the analytics cluster, which is running Yarn right now. We'll get to other cluster managers in a moment. In this Yarn cluster, we have a single gateway node, and on that gateway node, along with things like Knox and the name node, we have a process called Jupyter Enterprise Gateway. And all that Jupyter Enterprise Gateway does is manage multi-tenancy and the kernel lifecycle. The kernels themselves are kept off of this gateway node, and they run inside the pool of Yarn workers inside Yarn containers. So here in this example, we have 2 users, Alice and Bob. Bob is connecting through the multi-tenant enterprise stack. Alice has chosen to run the open source Jupyter stack on her laptop. And they connect to the same Yarn cluster, but because of Jupyter Enterprise Gateway's lifecycle management, now Alice's kernels are running inside a Yarn container alongside which is the same container containing her Spark driver, and she can scale out her Spark application by having other Spark executors run in other containers. And Bob can run multiple different kernels, each of which gets their own containers. So you see, with this kind of an approach, not only do we get security working, these processes are owned by Alice, these processes are owned by Bob, but you also get scalability because everything is down here in the scalable pool of workers. So if we looked at our graph from before the Jupyter Enterprise Gateway was all flat. Now that we can stick our kernels into every node of the cluster except for that gateway node, the scalability is purely linear. We double the number of nodes, we double the number of users we can support, or we double the amount of data each user can work with. And that's what we really need to be able to support these enterprise deployments. You want, as a DevOps architect, to be able to have as many users as possible in a single cluster. That way you get better sharing of resources, and now you also get better sharing of work, like the tasks that the users are working on. This was a lot of work, but we have amortized this work, all this development work, over multiple products. This has been in production use for several years now. Here's a partial list of the products this is in. That last one is for some stuff that's coming out in a couple of weeks, hopefully, that I can't talk about yet. But this is the core of IBM Analytics Engine, IBM Watson Studio, some of our on-premises offerings. Most of the analytics offerings that are embedding Jupyter Notebooks are also embedding Jupyter Enterprise Gateway because we really need it to be able to work with large teams and large data. In addition to making this available within IBM, we're also making this available outside IBM. We have open sourced this entire system. We've released it through the Jupyter project, through the Jupyter Incubator. You can find it on the Jupyter Incubator GitHub at this URL. We're currently at version 0.9.1. We should be coming out with 1.0 relatively soon because of some new functionality I'll talk to you about in the next slide, which is, initially we supported Yarn. Now with 0.9, we also support a different cluster manager. This is IBM's enterprise-grade cluster manager, IBM Spectrum Conductor. And now, with some code that I'll show you in just a moment, we can now run the Jupyter Enterprise Gateway on a Kubernetes environment. Code is there. It's currently in a branch. That should be merged in a couple of weeks and released as open source. Also, it's being used in active pre-production in IBM. Here's what things look like on Kubernetes. Very similar to the Yarn environment. Again, we can have Watson Studio as a multi-tenant environment for the notebook service front end, or you can have a plain old open source Jupyter stack. Anyway, everyone connects through the gateway, which runs on its own pod. Now we don't have to share that master node anymore because of Kubernetes flexible pods. And this, again, has the kernel lifecycle management and the authentication all running inside of here, and that's all that's running in there. So we can scale to hundreds of kernels if we need to with that one pod. The kernels themselves run in separate pods, one per kernel, and depending on what kernel specification you use, we'll start up a different size Kubernetes pod for each kernel. You may have a kernel that's running an image from Anaconda with an entire data science stack already preloaded. You might have a kernel that's got a TensorFlow stack, or you might have a kernel that's running Spark on Kubernetes. We've tested and integrated this with the Spark running on Kubernetes. So you can have an entire Spark cluster spun up on top of Kubernetes pods. And all of these can talk to your distributed file system through Kubernetes volumes too, so they all see the same image of the working directory. So that's how it works on paper. Let me quickly show you how it works in practice. So over here, oh, my screen has gotten much smaller. I may have to zoom in a bit. Here we have my Kubernetes console. And you can see on this cluster here, well, not that big, that big. On the cluster here, I've got a reverse proxy running, and I've got a copy of Enterprise Gateway running on two different pods on the cluster. So now I'm going to start up a Docker container on my laptop with an open source Jupyter stack. So the notebook server is running on my laptop, but it's going to proxy all of its kernel requests over to Kubernetes cluster. So all the kernels that I start from my environment, use my right hand, they're all going to run on the Kubernetes cluster in San Jose. So here's my Jupyter lab. And demo, please work. Okay. I just was too impatient earlier. So we have a Jupyter environment, which I'll make bigger so everyone can read it. Oh, and the reason it started up was because I forgot to properly shut down the demo. I did that last time, and so it auto-started all of my kernels. That wasn't nice. Let me shut down the kernels so it gets into it. Shut down kernels. Shut down kernels. And now, okay, now I've got my notebook running. The new notebook server is running on the laptop. Jupyter Enterprise Gateway is running all the kernels on behalf of this notebook server, but the kernels are running inside Kubernetes. If I look at my Kubernetes dashboard and refresh my list of pods, you can see it's still just as before. We just had that gateway pod and the reverse proxy running in a different pod. Go back to Jupyter Labs, and I can start up a kernel, a Python kernel that's configured to run a Python kernel on Kubernetes, and that starts up. And now I've got a Python kernel, and I can run some code and show my host name. And if I go back to my Kubernetes dashboard, that kernel is running inside its own pod. And I can start up a second kernel with a slightly different kernel spec that's going to be configured for a TensorFlow. If this cluster had GPUs, this kernel spec would pick a pod with GPU capabilities. In this case, it's just picking a pod that has TensorFlow preloaded. So I can import TensorFlow, and I can show the TensorFlow actually done imported. And I'm running on a different machine, and we can see that. And here again in the menu line. Now I have 2 pods running Jupyter kernels. I can, if I have a notebook task that doesn't need a whole lot of resources, I also have the option to just run a kernel locally in the pod with Enterprise Gateway. That starts up faster, so it doesn't have to start a pod. This would be mainly just for if you want to only display a notebook and you're running a kernel as a side effect of that. So you can see I started that third kernel and I didn't start a new pod for that. So I still have that level of control for small tasks. I can also run things that are not Python. Here's a Scala notebook. This takes a moment to start up because the Scala kernel's a little bit of a heavy-duty thing. There we go. So here's some Scala. And again, I can, get that crashed. Oh, there we go. Okay, now it's up. So just restart the kernel. There we go. Now we have kernel running. And we can execute Scala commands. And you'll notice in spite of that restart, Kubernetes should have still cleaned everything up, and yes it has. I've got 3 kernels running in separate pods and 3 separate pods for those kernels. I can also do Spark on Kubernetes. So here's a PySpark notebook. I'll start up. That takes a little bit of time because this is also running Scala behind the scenes. And it's going to be starting 2 different pods. One to hold the kernel and one to hold the Spark driver. So we're up and running. So we see my machine. There we go. Okay. So you'll notice, by the way, we have deferred initialization of the Spark context Spark context can take like half a minute to start up. So we start up the kernel quickly and wait for Spark to start up asynchronously. That was a big thing we had to add to product use. People get really annoyed when they click on the notebook and it takes 30 seconds for anything to happen. So now Spark should be started, and we can see our Spark context is running. If we look on the Kubernetes dashboard again, now we have the same 3 pods that were running before. Now we've got another pod for our new kernel for Spark, and an additional pod for our Spark driver. And if we actually ran a distributed job, you see more pods started up to run the executors. So you can see this is running the way we would expect it. As the amount of work I put onto Jupyter scales up, we start additional pods. I could change the type of pods and the size of pods that I run for individual notebooks. And lots of users could be doing this at the same time. You're really only limited by what's the total capacity of your Kubernetes cluster. So that's Jupyter Enterprise Gateway running on Kubernetes. Like I said, that code just went into our GitHub repository this afternoon. But if you go to the link, which I showed you on the slides, you can pick that up. So let me come back into PowerPoint mode again. All right, so here's the location of the branch. That should be folded into mainline and then released in a couple of weeks.
We can put that in the comments box.
Oh, definitely, yes. So looks like that. You saw a demo, and that's about all for tonight. So this has hopefully given you a good introduction to the 5 different stages of deploying Jupyter notebooks in the enterprise, and our own experience going through those 5 stages, and how at the end we came out into a happy place with Jupyter Enterprise Gateway. So hopefully by following some of these links, if you are in the process of getting Jupyter into your enterprise, you can skip a couple of these steps by going directly to either Jupyter Enterprise Gateway or a couple slides back, one of the other solutions that you'll find along the way if you do things the hard way. So thanks everyone for coming to my talk. At this point, we have a couple minutes for questions. So let's start from the left.
So you just contributed to open source. Are you planning to continue maintaining it, and is it the identical code that you were running at IBM?
Mm-hmm. The question for those on the live stream is, we've contributed this to open source. What's the relationship between that open source and what's used in the IBM products? The relationship here is what's in open source is exactly what's in the product. We follow a practice for this artifact of sending releases out into open source through Jupyter Incubator and then pulling them back into the product. That's so that we can maintain that integrity of the code base, number one, and also so that our clients who are using this software maybe on their own machines can understand exactly what's going into the stack that they're purchasing. So great question, thank you. Yes, so what you get is exactly what we're using internally in production. So in front.
So for the collaboration, you have to use the Watson version?
You can use the open source stack to do some collaboration.
Well, in your Bob and Alice example,
yes.
If there were 2 Alices, could they actually share?
Mm-hmm. If 2 Alices logged into the same Linux box and shared connections to a single Jupyter server on that Linux box, they could get some limited collaboration. They'd be able to see the same list of notebooks.
I mean, they logged into the same client box.
If they logged into the same, the same. So remember, there's the ugly stack.
Yeah, I'm going to the Bob and Alice thing.
Yeah.
So
but the thing you need to look at is the one that brings anger. There we go. Okay. So this part, if Alice and her friend Josephina shared this process, the open source version, they would both be able to connect to the same web UI. They'd both be able to see the same list of notebooks. The handoff between users wouldn't be quite as nice, but they still would be able to see the same image of the working directory. And when Alice pressed save on an open notebook, her coworker would be able to see that in a static fashion in the same environment. So there is limited collaboration in the open source stack. Obviously with Watson Studio we expand that quite a bit and layer some security and authentication on top of that. But it was very important to have the open source stack supported.
So maybe for later, is there a write-up of what collaboration doesn't work with the new gateway open source? I mean, what you can't do without Watson?
So you can't. So Watson is a hosted service.
I know. So that I'm trying to.
That lets you can share notebooks online. You can give a colleague elsewhere in your company a URL to your notebook, and because the service is always up and running, that's always there. With a copy of the Jupyter Notebook server that you start up yourself, you would generally start that up at the beginning of the day and shut it down at the end of the day, and you usually only connect to that over SSH tunnels. So it's not really intended for broadly sharing across the enterprise. If you did enough work, you could probably hack it, so you could make it work. A lot of people in academic settings who don't have stringent security requirements just make things work with the pure open source. But in the enterprise, we need to do things like integrate with our Guardian tools to get proper data provenance of the models that actually come out of this process. So we have a much more advanced collaboration facility there. That's great. Thanks for the question. Yes?
Is the interface to support different cluster manager considered stable enough now that if I check out the open source code, I can go add a Mesos cluster support?
So the question, again for those on the live stream, is the interface for adding additional cluster managers we have later on here. We are running currently 3 cluster managers, remember? Come on. There we are, okay. So we started with Yarn, we added Spectrum Conductor, now we have Kubernetes. It was designed from the beginning to support adding Kubernetes because we knew Kubernetes would be there, so it is pluggable. The chief architect on the project is sitting in the back there. Hey Luciano, you want to raise your hand? And if you want to talk to him after, we can get a detailed answer to your question about adding Mesos support. I don't see any reason why not, but Jupyter is a fairly complex beast, so expect it to take a while. Kubernetes certainly took a while. But thank you for the question. Any other questions from you? Yes, please.
Yeah, it's not related to this, but I think for the enterprise, the version control also is very important. Have you done any improvement for the version control of the notebook? Because currently it's a JSON files. You could do the diff and you could do the version control, but it's not very intuitive.
That is true. The question was about what about version control.
Yeah.
There's some limited versioning facilities in Watson Studio,
Okay.
but I think version control for notebooks is in general an area that could use some more work. When you put IPython notebook JSON files into Git, Git doesn't do a very good job with those.
Yeah.
So that's definitely an area that could use some additional work. Some work has been done in the product. It's been fairly pragmatic to date, though. Yes, in the back.
If you want to automate notebooks, so like from cron jobs, how would you go about it?
If you wanted to automate notebooks from cron jobs, how would you go about it? Luciano is smiling because he has a demo of just that he can't show you. So there's a related project that we could show you, but I don't think I have the deck that we did in collaboration with Netflix, if I recall correctly, out in the open, about turning a notebook into a cron job. One of the things that notebooks are great for is acting as a dashboard. Also, in a deep learning setting, if you have a notebook that will consume the checkpoints from your deep learning training job, you can use that to get a much clearer picture of what's going on than with something like TensorBoard, because you can actually run data through the model. So really good for being able to run batch jobs, or maybe even being able to run things you would normally run a script for as a notebook. So you can do that with Jupyter Enterprise Gateway by using Jupyter Enterprise Gateway as a programmatic job submission API. Basically, instead of having a notebook stack on the other end of that connection, you have a program that is periodically scheduling jobs and just telling Jupyter Enterprise Gateway to start a kernel and sending a job over. So A great question. Yes, and something that comes up a lot with an idea. Have I run out of time?
I think we need to stop the questions right now because we have another talk coming up, but you're
Okay.
going to be around if people have more questions after.
I will definitely be around. Yes.
So can everyone give a round of applause to Fred? And our next talk is on Airflow, which is a full Apache project, 2 years in production. And they're going to be talking about that, and it's all about scheduling and workflow orchestration. So give us approximately 30 seconds to set up. It shouldn't take any longer than that. Did you put the other?
Would you ever do
Thank you, everybody. So I'm Shaker. This is Robert.
How's it going?
Okay, so last minute change in the title. Robert insisted on that. I don't know how many people will get the reference, but it is Star Wars time, right?
I was going to add that to the quick poll.
So just before we get going, just to get some sense for how many people here work with Hadoop or any. Okay. How many folks use open source workflow orchestration schedulers? All right. Anybody using Luigi, Pinball? Okay. All right. How many people use cron? That's not everybody? Oh, okay. All right. So, cool. So there'll be a few things to cover for multiple people here. So, you want to get into introduction, get that out of the way?
Sure. My name is Robert Sanders. I'm a big data manager and engineer at Clairvoyant. We'll talk a little bit more about what we do at Clairvoyant, but I mainly work with a bunch of clients for big data purposes. So that means Hadoop, Spark, anything that runs on top of the Hadoop data stack. That also involves Airflow and utilizing Airflow for scheduling operations.
Cool. So I am the CTO and one of the co-founders of Clairvoyant. We are actually based out in Phoenix, so I came prepared for the weather. Robert didn't.
It's
so
100
it's
it's
only
100 degrees in Phoenix
out
right now.
We'll skip through most of this, but just to talk about why our journey of working with Airflow over the last couple of years. I actually started using it right when it was still being built by Airbnb and not part of the Apache project. So our focus predominantly is around data engineering, data science. We do a lot of data products with focused on user experience too, to bring it all together, not just toil away at building a bunch of pipelines, like to control the end-to-end user experience. So over the last 7 years, built, I don't know, maybe thousands of these pipelines. So quite a few learnings there. One of the other things, in a past life, built a predictive analytics company. It was mostly in the higher ed space, lots of Hadoop. We started using Airflow there actually. We'll go into a couple of details there. But today, one of our main usage other than client engagements is in a product that we are building for a data security solution that allows discovery, securing, and monitoring of sensitive data in your environment. And we'll talk in two contexts, one as to how we use it for our own product behind the scenes, Airflow specifically, and then also how in a bunch of some of our client engagements, what we do there. So let's get the agenda, we can go into more detail there. So how did we come about this? Here's the actual story, somewhat edited, but I think this was early 2016. So one day I just happened to run into Airflow, spent a couple of hours, that's all the time I got then, and maybe that's all I could do with it, but after a while, asked Robert, forced is what he tells everybody today, but asked Robert to spend a little bit more time. Now, before we get into the final joke, hopefully, now the story has become, I just wanted to play with some new cool tools. That's why I forced him to do this. But on a serious note, hopefully, over the years, this 5 years, 6 years, I would love to say I built a lot of expertise with things like Uzi, cron, maybe doing a lot of work with quads and doing a bunch of jumping through hoops to make it work with Java and quads and build these sophisticated schedulers. But after a while, I realized that's folly. I mean, it's not building expertise, you're just yak shaving, right? So it's, you can sometimes get into the mode where you think you're doing something cool, but it's actually just pretty useless stuff. So what we needed, as you can see, 4+ years of working with Uzi. How many people have worked with Uzi here? So at least a couple of folks understand the feeling. But as I said, tried to build expertise, but gave up on it. So what we needed was a scalable, huge open source fan, so nothing like Control M would ever work for us, right? Not that it's a bad product, but still. Needed a scalable open source and something that's been oft ignored in this space, a user-friendly engine, both for our internal needs, but a lot of what we do for our clients too. And the key thing being minimize the time to help monitor, discover problems with your pipelines, and get to the root cause much quicker, right? So we'll talk about a few things as to how we can achieve that along the way. So I won't, in the interest of time, it's a rich landscape. There are a couple of GitHub links which will probably list out 24 of these, half of them, if not more, open source ones. Personally, the only two that I worked with before was Uzi, and before we landed on Airflow, spent about a week on and off on Azkaban. So I'll skip the evaluation criteria, all of those pieces. We'll just get to the stage where we said, okay, we are picking Airflow. It has a pretty UI for its class of pieces of software. Now, for those who don't know what Airflow is and wondering what we are on about, so Airflow is a open source tool to programmatically author and schedule and orchestrate your workflows. So if you've ever worked with DAGs and building jobs which have multiple steps and processes along the way, dependencies, you don't want to start step 5 without finishing step 4. So Airflow is a tool that you should be looking at. The biggest reason, other than hating XML, but workflows can be expressed as Python code. For those who actually have attained the nirvana of what that could potentially mean, this is huge, right? So this just means now, for good and bad, we'll talk a couple of things about the bad, but for good, you can essentially programmatically and dynamically generate workflows and change the behavior of your DAG along the way. provides great monitoring tools and lots of visibility and insight. Started off as an Airbnb open source project and joined the Apache Incubator project early 2016 sometime.
So, question ended up coming up, why use Apache Airflow? I think it was me who asked that. So after he kind of handed it off to me, that was up to me to determine that. And ultimately we kind of landed on, after doing some research, these are some reasons why we ended up wanting to use Apache Airflow. One, the processes are actually very lightweight. They're called Python applications, and really the daemons that are running in the background are pretty lightweight. They don't require a lot of resources. Really the main processes that require a lot of resources are the actual jobs that run on top of, or run as tasks. Other things that we found were very useful was that, well, as Shaker already mentioned, the actual descriptor of the workflow is all in Python, so that can all be very dynamic. So you can dynamically generate some workflows, which we'll be going into one use case in which that will hopefully illustrate why this is useful. It has more useful, more flexible execution, meaning that we'll be going into some detail on this as well, but there's different ways that you can execute your individual workflows, either sequentially or on some form of a cluster or locally on your individual machine. Showing up here is some of the individual web interface tools that you can see. So you get a list of all the individual DAGs, as well as the ability to drill down into those individual DAGs and see exactly what how that is actually wiring up all of the individual tasks. So it's a feature-rich web interface. This is only some of the things. We'll be showing a few more. But they also do provide the ability to show how long some of those tasks are taking, history of how many times a particular task has failed. You can drill down into a lot of that and hopefully diagnose problems with your actual workflow. In addition, the actual workers themselves and the entire infrastructure can scale horizontally and vertically. We'll be showing a little bit more how this can be accomplished. And it's extensible, meaning that you can build more or less that is plugin based. So you can build additional types of executors and represent those as just plugins.
We're not even in the demo stage and already
locking my laptop. So, I mean, that's just from also an executor perspective, but you can also build other types of operators, and those all can get represented as plugins. We built a number of plugins that we find very useful at our whenever we're doing anything in particular. So we'll be talking about some of those. So just talking about some of the building blocks before we actually dive into kind of the overall architecture. These are some of the individual components. So on the far left there we have the executor, how the individual tasks are going to be executed on. So I kind of gave some examples. One is executing that on a cluster, whether that be Mesos or Kubernetes is coming soon. So how exactly are these individual tasks going to be executed? Another is a queuing service. So in the event that you're using a particular kind of executor, those tasks need to be queued in some way. So the queuing service is going to be helping with determining when a particular task is actually executed. The scheduler, that will be the process that's constantly pulling to determine whether or not a particular task needs to be scheduled to be ran. So it pulls every X number of seconds, that's a configurable value, and ultimately scheduling a particular task to be ran and pushing that message into the queue, also kind of depending on the executor as to how the scheduler actually operates. The web server itself is basically just a very nice, shiny web interface on top of the Metastore, which showing next. We'll be showing a little bit, doing a little bit of a demo on the web interface itself to show what kind of stuff you can see. I already kind of mentioned some stuff, the ability to see how long tasks are taking, that kind of stuff. Then the Metastore, naturally just storing data. Individual operators, so operators are actually implementation or tasks that will be doing a specific type of operation. I'll be going into some detail on those individual type of operators. And then we have the workflow itself, or the DAG, the directed acyclic graph. If you're familiar with like Spark or that particular keyword, is basically just basically it's the same thing. Basically just a series of tasks that don't loop upon itself, that are all directed, basically edges and vertices that don't loop back upon themselves.
And the reason to highlight some of the building blocks, we won't be able to maybe cover all of them, but the key takeaways, so a course scheduler, executors, right? So as important as things are to run on a distributed cluster, in a distributed and cluster environment, one of the things, at least I'm a little biased to, is it should also run in a single node deployment. Especially as you're getting going with things, you want to minimize some of the complexity. You want to be able to run a bunch of stuff locally on your laptop. So while that's not the sexy thing to do anymore, with the whole downside of laptop data science, but there's huge benefit in running these things locally. So you get to pick which ones of these you want to run in either a single node deployment or a clustered environment. And we'll actually go through a couple of those details.
Yep, so next just talking about executors, so talking about what exactly are executors and what are some of the current ones that are available. So what exactly is an executor? It's basically the mechanism by which tasks are actually executed, get ran on. So these are some of the base executors that are available right now. You got the sequential executor, basically is what it sounds like. It executes tasks sequentially, one after the other. A local executor is basically just running it within local mode, like Shaker said, running it on your individual laptop or on a single machine. Basically, that utilizes Python's multi-processing engine to just run each task as a separate process. Then you have the Celery executor, which basically utilizes Celery, which is another kind of multi-processing engine. And this is the one that we usually utilize a lot and actually distribute into production. We'll be showing kind of what a diagram of that would look like. Mesos executor, utilizing Mesos clusters for actually executing individual tasks. And coming soon is Kubernetes executor, which should be coming out in the next iteration of Airflow. So coming soon for that.
Out of curiosity, anybody, how many folks are actually running Mesos in production?
Okay, so a single node deployment that we usually set up involves using Celery as the actual executor framework. In this particular case, we have a number of the individual building blocks that we talked about. We have the scheduler, which is actually just going to be polling every now and then to determine whether or not a particular task needs to be executed in whatever workflows are available. Once it determines that a particular task needs to be scheduled, it will push that message into the queuing service as well as an entry into the Metastore to let it know, hey, this particular task is starting to be ran with a particular state of queued or in progress, running, whatever it may be. So the scheduler will push a message into the queuing service, and then the executor, which is basically the worker. So there's one, I listed there, there's 1 to n, basically one to many number of executors that are available. This can be configured. So these are individual workers, worker processes. So each worker will bring down a particular message from the queuing service, and that message just basically is what command needs to be executed. And it'll handle executing that individual task and update the Airflow Metastore to say what the result of that is, whether or not it was successful, whether or not it failed. And the executor will also handle pushing any emails or whatever authenticate messages, notifications if there's any failures or anything at that point. The web server is also available to see whatever is going on within the Airflow, within the Metastore. So you can see all the tasks that have been queued, started, in progress, waiting for downstream processes to be complete. So that's available as well. And if you want to force start a particular task, the web server also provides that kind of mechanism to automatically push a message into the queue and start up a Metastore. So this is kind of the overall landscape of the single node distribution that we usually set up. If you want to break it down and start to scale up a little bit, you can start to essentially designate multiple worker nodes or a particular master node. So in this case, we have multiple worker nodes with, again, 1 to n, worker nodes with 1 to n executors, and the master nodes will all contain the master node will contain all the master processes involving the scheduler and the web server. Again, all basically the same functionality, but now it's all distributed across multiple machines. So this means that if you want to increase the parallelism, you want to have multiple tasks, more than X number of tasks running, then you can actually just add another node, or maybe increase the size of these individual machines and then increase the number of actual executors that are running on on that machine.
So in a couple of instances, just to draw some parallels to even some of the conversation from the earlier talk, these could be, while a large part of everybody using Airflow is typically focused on data engineering, but one thing often ignored is the fact that it can act as an enterprise scheduler. So you could not have Hadoop in the picture or anything related to that and still use this for everything else from a orchestration and scheduling perspective. Right from just running bash commands up to sync. I've seen people sync databases right from production to replicas down to dev and QA using Airflow jobs. So another takeaway would be this isn't just a Hadoop or a data platform-centric tool. It's an enterprise scheduler.
I have a question about the Metastore. What kind of persistent engine does it support?
Good question. In fact, let me talk about both the queuing service and the Metastore, what kind of engines those can be. So the Metastore, under the covers, Airflow is utilizing SQL Alchemy. So it's basically whatever SQL Alchemy can connect to. So that involves MySQL, PostgreSQL, and also SQLite, although SQLite is not supported when you're using multiple or Celery, so multiple processes trying to write to the same database. So those are the primary types of metastores that you can utilize. In addition, the queuing service. The queuing service can be, we primarily distribute it with RabbitMQ, although Redis is also another very heavily used queuing service that's used. And then there's also an experimental version where you can use MySQL, not recommended for production, at least at this point. But those are some of the queuing service. We've also utilized AWS's simple queuing service for leveraging that. So now that you have the infrastructure all set up, how do you define a workflow, and how do we ultimately get something running in that environment? Well, it's fairly straightforward. This kind of shows the individual sections. Well, we just need, but again, this is just a Python file that we ultimately just create and load into a location within the local file system. So first we import all the necessary libraries. Here we only really need 4. We define the high-level global variables that are used, so the default arguments. Right there, we just define who the owner is. That's basically going to be something that's labeled within or available within the web application, just to say who the owner of that service is. So that way, you can, if any jobs fail in that area, if you have a particular DevOps team that's constantly monitoring Airflow, then they know who to talk to go into for why that failed. The number of retries, so individual, you can set a global variable for how many retries you want to be you want to redone, you want it to redo. In this particular case, it's just retrying once. You can set that to 0 or however many times you want. And then later on, when you're defining the individual tasks, you can override these values. So say a particular task, you want that to be ran maybe 3 or 4 times or 0 times. You can set that in that individual task. So this is just a default set of arguments for the individual operators. So we've defined the individual, and there's a bunch of other arguments that you can specify. There's just look at the documentation. You can see a bunch of them. Then we're defining the individual DAG. So we provide a DAG ID, so just some identifier for that particular DAG, which will just be displayed within the web interface, passing the default arguments. And then our schedule interval is basically just the, it could be one of two things, either a cron expression, so you can still utilize your favorite cron expressions for those of you who use cron, or there's also a more simplified, more English look at it. There's basically there's something provided by specifically Airflow. For example, you can do like ampersand daily, ampersand monthly. So basically, corresponding daily would mean that it runs daily, I believe, at noon or midnight. UTC, and then monthly would be every month, first of the month. So however often you want this particular job to be scheduled, that's how much you can set it. The start date is basically just when that job actually starts. So by default, we're just passing in exactly what the today's date. Next section, we're just finding all the individual tasks. So right now we're just utilizing the bash operator. I'll be talking about what these different operators or what different operators are available. But the bash operator is basically just executing a bash or bash statement. So we're defining 3 individual tasks, and then below that we're setting the relationship between those individual tasks. So basically you just utilize the set downstream. There's also a set upstream functionality. Basically that'll just set what their relationships are. And at the end of the day, with regards to this particular relationship, we get just a straight line of task 1 is dependent, task 3 is dependent on task 2, task 2 is dependent on task 1 to be completed. So that's defining a static workflow, but what if we want to create a dynamic workflow? So maybe based off of some argument that you pass in. Well, this is just a simple way in which you can do that. Assuming that you have your DAG, object defined, you can iterate through a list of, say, a list of objects, and create a single task for each object that's inside of there, and then set the downstream task to the one before that. So you could just iterate through a list, create a new object, and then add that to the whole dependency relationship. And this is basically the exact same thing as what we have done before. So now, if you wanted to create maybe 15 individual tasks, it's just a matter of updating one individual value.
So this is where earlier I was referring to. So this is a pretty powerful paradigm. At the same time, you can do some really stupid things with this. So myself included. So somebody built a, essentially if you were hand coding a Python workflow orchestration without using any of the operators and the conditional stuff that Airflow offers, you can pretty much execute everything here as one big task. At that point, why are you even using Airflow other than the scheduling aspect? But it takes a little while to get a good flavor for how you want to use the inbuilt operators, the conditionals to build your workflows. But one rule of thumb over a period of time, at least something that we learned was, as you look at these things, these are to be, if you have a set of workflows or tags which seem like fairly overlapping or consistent, except for a few things changing across them, just extract, just like any other abstraction, extract them out into a template and use these kind of the dynamic capabilities of the platform to customize each instance of the workflow. So if every single workflow that you're building is of this nature, you probably are maybe over-engineering a little bit, but if you have a bunch of workflows which follow a similar theme, and one classic example I'll show in a bit, but that's where the real power of using something like this comes into play.
So we already kind of showed one type of operator, which is the bash operator, which is basically just an operator, a particular task that just executes a bash command. But more broad than that, there are three types of operators. One is a type of action operator. So an operator that will perform a particular action at that given point in time. So examples of that are the bash operator, SSH operator, Python operator. These so the bash operator will execute a bash operation at that point in time. SSH will SSH onto a particular machine and then execute a particular command on that machine. And a Python operator will execute a particular Python function. So these are examples of operators that will perform a particular action at a given point in time. Another type of operator is a transfer operator. So this is basically at a high level, it's basically transferring data from one location to another. So an example of that is the Hive to MySQL operator, and vice versa. There's the Hive to a MySQL to Hive operator. While these operators are available, these transfer operators are available, how they'll work under the covers is they'll basically copy all the data from the source system, copy it to the local machine where the executor task is running, and then copy it up into the final destination. So, for example, if you're familiar with Hive, that data can be in the realm of terabytes. So bringing terabytes worth of data down to a particular machine that maybe only have a couple gigabytes, probably a bad idea. So use those transfer operators wisely, would be my advice. Sensor operators, basically these are operators that will just poll for a given amount of time. And once a particular condition is met, then it will actually allow downstream processes to execute. This is particularly useful if you're waiting for a particular condition to be met. So say that you're waiting, so you have an ingestion pipeline. That's basically taking a file that shows up on a daily basis, take that file and then load that into your into your Hadoop cluster. I use Hadoop because I'm big data. So maybe push that data into Hadoop and then do some other processing to load that into a final data store, whatever your final data store is, whether it be Hive or HBase. In that case, you can have a sensor operator that will just be waiting for that particular file to show up. So that's why those individual, that's the difference between those individual operators. So again, have some examples of each of those individual types of operators, but there's many more that I have that are not just listed there. I believe there's about 36 operators, so you can take a look at those, and also the extensibility of Airflow itself provides the ability to create new operators as you'd like. So if one doesn't exist, you can just create it.
So one of the use cases that we'll talk about two use cases, right? So contextualizing a lot of this into why did we want to put Airflow into this? So long story short, what we wanted to do was, so from our tool, which we'll go in and take a look at really quick, we could connect to a bunch of enterprise databases and scan right from what could be one table in one schema to hundreds of tables across hundreds of schemas. So an example of what I typically call a deep DAG, right? So it's 2 or 3 steps, but executed possibly anywhere between 1 to up to 1,000 times as part of an overall job. Broad DAGs would be where you have a workflow which has 20, 30, 40 tasks orchestrated. There's some branching stuff also going on. But this particular use case that we're looking at is an example of a deep DAG of that nature. We did actually start with just generating some of the XML config from Uzi, because that's what we were most familiar with at that point. But pretty quickly, it became a nightmare from a visibility perspective. So let me just, to help contextualize this, so let's say I just create a new data source. So you can connect to a bunch of stuff, but the real fun comes in when So I'm looking to create an inspection profile. This is the one that does the scan. So everything that you see here, once, hourly, daily, weekly, is proxied over to the Airflow representation of that. You can just give a custom cron expression. But once I select a, let's just do S3 data source, see if there's, oh, no, I don't think there's anything there. All right, so right now, I just want to run the scan against one table. If I save this profile and say, okay, I want to run this once, versus I want to run this hourly and select, let's say, one entire database, which means 31 tables got selected. Behind the scenes, it's just one template, DAG, for the workflow, which is handling both scenarios, right? So what we are just passing in is some of this metadata and the arguments, which allow us to go iterate over this profile's configuration, and then create the workflow dynamically. This is just done once, of course, when we save the profile. But the flexibility here, of course, is we don't have to go manage any of that, any of the dependencies, the orchestration of all of this. Once you build your template in an effective fashion, Airflow will go handle all of that for you. Again, I know a bunch of folks may not have worked with Airflow, so some of this could be new. So if you have any questions, feel free to jump in.
Yep, so we go to the next use case. So this ended up being one of the first implementations of Airflow we did at the time. So this was one particular case that we saw being very beneficial to utilize Airflow rather than Oozie at that given point in time. And you might be able to see that just based off of this particular description, which based on, this is for one of our clients. They came to us with this problem statement, and we helped them to try and fix it, to try and actually implement it. So they had 23 databases with a grand total of 1,226 tables. They wanted all of that data to be ingested into a Hadoop cluster and ultimately loaded into final Impala tables. So many of these tables would actually be consolidated into the same final table. So that was our problem statement. And then so we have some other requirements, including the ability to add more tables, as the case may be, because the 23 was just the initial set to kind of prove out the whole use case. They eventually had a lot more. So they wanted something extensible for them to be able to add more databases to this. And then at the end of the day, we would ingest all this stuff on a daily basis, and then they would send out a report to say which ones had failed, which ones succeeded, how much data was ingested from each database. That was the whole thing about how much about the final report. Our solution ended up being that we created a DAG that would just dynamically generate a workflow based off of data within a metastore. So this ended up being the architecture of that particular DAG. We have, within our Airflow metastore, we have basically some additional tables that we've added on top of the additional metastore, which has a list of all of the individual table databases, the tables, and then credentials for accessing those. And basically, we have our entire, it'll just iterate through that list and generate a series of tasks to extract the data, utilizing Scoop in this particular case, because the data was, it was in multiple different types of tables, but all of them could be connected over JDBC. So that was another challenge that we ended up having to overcome, utilizing, creating something to be dynamic in nature to utilize Scoop. And then perform any transformations, loading, and then clean up any temporary tables or anything that was created at that given point in time. So this ended up being the overall high-level architecture of the DAG itself. And this was kind of the resulting DAG. So looking back at the actual Airflow web interface, you can see that these are just snapshots of individual DAGs of the same DAG. This is just a small section of it, and here it's barely readable. That's not even the entire DAG. So each one of these are individual ingestion pipelines for one individual table. So this is where I feel that Airflow kind of shows where it's actually very beneficial with the ability to dynamically generate workflows and the ability to add more, pretty much ingest many tables at a given point in time. So after doing this this particular implementation, after our first implementation and even our second implementation, these are some of the things that we had learned, including some best practices, which we'll go into in another slide. But this is kind of this is my second section to complain. So one is that Airflow didn't exactly have a lot of support. At that given, nowadays, it's actually pretty well supported by the community. There's actually a lot of content on Stack Overflow, but given the point in time when we got involved in this, it was still very new. So there wasn't all that much support available out there, even from the community standpoint. It's not like Cloudera where you can get a license from a particular vendor to help you out with any issues. You're pretty much left to your own devices to help work through any problems. The documentation, while it is pretty nice, it's not versioned actually. So if you go to the latest Airflow documentation, it'll show the latest version of the documentation. It doesn't provide you the ability to go back to, say, we still have some Airflow instances that are, the current implementation is, the current version is 1.9, that's the latest version, but we still have some Airflow clusters that are running in 1.7.1.3. So if we wanted to go back to that version, we wouldn't actually be able to see that. We'd have to kind of be smart enough to look at what the differences are. In our cases, that usually involve looking at the source code itself. Being that it was an open source technology with a number of different contributors from not one particular company, there were a lot of little bugs with it. Certain operators wouldn't work until you applied a particular patch. There's some odd behavior. For example, in 1.7.0, there's a weird thing where if you deploy a scheduled DAG, it automatically creates 3 backfill tasks already, running instances of those workflows. So that was some weird hiccup with the implementation. So there's a lot of that little stuff in there. Future iterations fixed a lot of that, so it's a lot more stable. But that was just some weird stuff that we were like, was it a problem with how we implemented? Is there a problem with our, what's wrong? So that was just a lot of stuff that we had to kind of trudge through. Monitor performance with charts. So these are some of the charts that I kind of mentioned. These ended up being instrumental in us determining how effective some of these individual tasks were. It helped us diagnose a bug with one of our individual tasks where it kept getting taking more and more time to execute a particular task. Eventually, we realized that that particular task was just not operating correctly. It was just how we implemented it. So that was something that was very beneficial. Tune the retries, and this speaks to another thing that we're going to be talking about as far as best practices, which is making sure that your task is idempotent, meaning that you can execute it however many times. At the end of the day, the result will still be the same. So, for instance, if we have an ETL pipeline with, you want to retry an ingestion pipeline maybe twice. If it fails the first time, some data already exists within there. So your job has to be smart enough to be able to wipe that data out before retrying the ingestion. So that was something that we had to implement as well. And then parallelism. So by default, it has parallelism set to 8. So meaning that there can only be 8 parallel tasks going on at a given point in time. So tuning that ended up being helpful in utilizing the full extent of the cluster. In that particular case, we had 1,000 tasks that could be ran at a given point in time, but because we only had 8 parallelism, I use caffeine. So we had 1,000 tasks that could be going in parallel, to ingest data from each of the individual tables. But because we only had parallelism set to 8, it could only do 8 at a time. So that left a lot of resources. Basically, we weren't utilizing the full extent of our cluster in our local environment. So
that's also another thing to consider from a multi-tenancy perspective. If you have a lot of consumers or client groups which have extremely different workload patterns. This is one of those fork in the road thought process where you want to see if you still want to run one cluster, do you want to run multiple clusters, do you want to leverage pools, things like that. So it's not just a matter of tuning parallelism, it's also how do you want to take an approach of multi-tenancy versus operational simplicity of just isolating those workloads just by running separate clusters.
So this leads into best practices. So best practices that we've determined over utilizing that. And a lot of this stuff is stuff that's best practices that can be extended to any type of ETL pipeline, but especially so in Airflow because it does these things very well. One is load data incrementally, so don't just try to ingest data from a particular table again and again every single day. Try to see if you can just get the delta's worth of data. Airflow does provide some functionality for this sort of thing. You can pass, there's some placeholders that you can pass into the actual bash operation to get like the last time the task was actually executed. So you can theoretically just take that individual task and then pass that into whatever function you say, like, okay, give me the data from this point and later. So that's an example on how you can do that with Airflow. Process historical data with backfill operations, so that kind of feeds into loading data incrementally. So Airflow does provide the ability to backfill data. You just need to set the start date to a particular time, and then at that point it'll determine based off of your schedule. Okay, it's ran daily, so you set the start date as 5 days ago. It'll create 5 individual DAG runs to ingest data for those individual data segments. I already talked about enforcing idempotency. Okay. Execute conditionally, so there's the ability to do branching type of operation. So if a particular condition is not met, then skip a particular execution of a series of tasks. Utilizing alerts is very, very crucial. Automatically by default, Airflow provides the ability to send email alerts, but it also does have Slack integration, so those of you using Slack can have all your data pushed into a particular location in Slack. Sensor operators, I kind of talked about that a little bit, and then building validation into your workflow. So making sure that at a given point in time, you might be expecting 1,000 rows to have been ingested, but if 999 are only there, then you want to stop right there because otherwise your downstream processes will be polluted with inconsistent data. So building that kind of validation into your workflow is very crucial. And then doing some testing. Should we skip this part?
Yeah, let's just spend a minute on this because this is one of the places we had to extend what came out of the box. So let's just spend a couple of minutes and skip the next.
Yeah, so scaling and high availability. So now that you have your cluster all built out in the original infrastructure that I talked about, how do you scale things and making sure that things are highly available? Well, I talked about making sure that there are a multiple number of workers. That's an easy way that you can ensure that your workers are highly available. You just create multiple of those. In addition, the web servers can act in the same way. Just create multiple machines, each with a web server instance running on it. So therefore, in this particular case, if master node 2 goes down, at least you still have one operational that you can hit with a load balancer. But the scheduler, on the other hand, does not allow multiple schedulers to be running. So therefore, we have to find an alternate solution for that one. This was something that we had ended up working on to build our own custom daemon, if you will, that runs in parallel with the Airflow instances. Basically, it takes over startup and shutdown of the scheduler itself. It runs as daemons on all of your individual master nodes. You just need to register where all your master nodes are, and it will ensure that at least one scheduler is running on each of those, on one of those masters. Okay.
Just a question.
Yep.
You use Zookeeper for that, or build this in yourself?
So the question was Zookeeper or build it ourselves. So it utilizes. So there is the ability to utilize Zookeeper as the election for which one is actually the active scheduler failover control, because the other one will go into standby. But it also has the ability to utilize MySQL as its election.
Yeah, just as a
lowest common denominator. In most instances, we just use the MySQL one because while there are Zookeeper instances available typically in a Hadoop environment, but it was yet another dependency that we didn't want to rely on. So there are still certain instances where this will potentially fall down if you just rely on MySQL. But it just covers, it takes you into the 99.99 percentile instead of the 95 percentile if you just rely on a single active master. Okay.
So, yeah. So, I can handle deployments, so I'll just go through this. Should we just get this one? Are we pretty much done? Yeah?
You guys are getting to the end of this.
We like talking about this.
I understand.
Okay, so, okay. Let's skip that. Let's just say questions.
So have you figured out any best practices when you have deep pipelines?
Deep pipelines.
In terms of how you do sensors from one to, external sensors, how you connect one to the next when it's large.
Okay. So
that was a problem in the airflow a year ago. Nobody really knew how to do it.
So, sorry, just trying to understand. So, like a sensor that would actually be like a number of subtasks within it, with the
multiple dependencies.
Yeah, there's multiple. It's not a linear DAG.
Yeah.
Like it's a complex waterfall with lots of things coming together. You have to have sensors to wait. If 5 out of 6 inputs are ready, you still can't run the next step.
Yeah.
You need sensors. There's a lot of ways of doing that.
For most of our instances, we just ran into like in production, at least, we didn't have many instances where we had more than 2 corresponding inputs. So never noticed that ourselves. In like a lab environment, we kind of push things through, but these are just running for a day or 2, so we didn't run into anything. But the real kind of problems we ran into sometimes was even with the 2, as you have like, the 1,000-foot view you saw, the 10,000, 100,000-foot view, there are probably 16,000 instances of that, pretty much. And a couple of times we saw that the scheduler would just bottleneck on it because of just the sheer number of instances of those. So one of the things we were doing there was running too many things. This was a single node deployment, so we just had to split things up and separate stuff out. But most of those instances were more resource constrained than issues that we saw.
Before you answer your next question, I know some people are leaving, so before people leave, I just wanted to say thank you for Workday for giving us the space and allowing us to have this here. So just a quick thank you Workday. I know. Please you have questions.
Does workflow has a airflow distinguish between a pull-based versus push-based triggering? For example, let's say in this DAG, one of the vertex, I need to do a backfill because of bad data. Okay. Is there a way to just run that backfill of that vertex and then trigger a cascade of backfilling of the other dependent jobs?
So there is a way to, that would have to be individually by the individual tasks. There is the ability for a particular operator to execute another workflow. So there's another operator that will actually trigger another workflow. So you could kind of build that kind of thing in. So in that case, that would actually pass in, say, the amount of time that the timestamp or the time segment that you're actually ingesting data for. It could pass that kind of information into the actual downstream workflow that you're actually triggering. So that's a way in which you can do that. You just need to trigger a backfill for one individual task, and then it'll handle cascading or sending all that information out to the downstream ones. If you don't have that kind of thing, then you need to do it individually for the individual workflows.
So how do you handle the inter-DAGs communication?
The inter-DAG communication?
Yes.
So there's no communication necessarily between the DAGs themselves. There's intercommunication between tasks within a particular DAG. And there's a technology that they have called XCOM, cross communication between tasks. So you can pass in that information. If you want to have cross communication between DAGs, then that kind of information can come from like just pushing data into a meta store and ultimately accessing that data.
Yeah, that's also probably a good reason for looking at sensors, so you're writing the output and then you're doing something else off. But it will all be external to the actual process.
Yep.
So are the sensors happening inside an executor, or do they run in the scheduler?
They're handling as an executor.
Okay, so they tie down an executor slot.
Yeah, they will. Yeah. That's one problem that you might come across is if you have like, that was one problem that we had. There was multiple running instances of a sensor, and that was pretty much bottlenecking.
So you get a deadlock if you're not careful.
Yeah.
Yeah, so there won't be any active tasks because a lot of those slots are just getting. So that's kind of where now you can do the parallelism, do all that stuff, but also leverage pools to isolate those kind of. So another way of multi-tenancy simulation.
So it's assumed that there are no cycles in a DAG.
Yeah.
But what ensures that there are none?
Essentially, Airflow itself, when it's compiling the DAG, it will determine
But
whether or
since
not there are cycles.
last I checked, you could actually have two DAGs communicate to each other. One could effectively call the other,
Yeah, it could actually trigger the other DAG. Yeah.
which then could form a loop.
So, I'm not sure how it handles like, okay, this one triggers that DAG.
Well, I mean,
Yeah.
what usually happens is there's an error path. And the error path calls something which calls back into your system.
So the error path in this case, it's actually going to be triggering another workflow?
Yeah.
Okay, so I mean, in that case, it's not going to trigger back the parent workflow again though, right? So, or it depends on how you.
Well, it may trigger a duplicate. There's no reason. I mean, I just want to know if, do you have enough?
There's nothing that's going to stop you from doing some of those things.
Mhm.
But it's also, I don't know if, in most instances, that's almost like you gotta do something deliberately to get into that situation.
You'd be surprised, but I just want to know. But it's a
I'd say
I mean, in
never say
theory,
never.
it can detect if it's passing context along.
True, especially if, if that's a way, I've seen somebody do that for retries.
Yeah.
Instead of inbuilt retry, use the error path to then do something and then kick it off again.
Exactly.
But that's one of those things where, fairly quickly at least we kind of started realizing, you want to stay away from a couple of those things, trying to and stick to leveraging some of the inbuilt capabilities as opposed to distributing that out externally.
In your talk, you mentioned UTC. Is that a hard dependency? Because usually a lot of the cron style schedule I've seen is local time, whatever the time zone the executors are set on. And also if it supports non-UTC, how does it deal with like all this daylight saving moving forward and backward when it's daily?
So that's something that's configured internal within Airflow itself. I don't believe you can change the timestamp as or the time zone itself. Not sure if it utilizes long time zone, but it should be utilizing UTC and should be released. Yeah, it is.
So you mentioned that the transform operator does some caveat on the memory stuff.
Yeah.
So what are the options? Do you need to load the data from Hive to other databases like RDBMS?
Yeah.
Even do like incremental load, sometimes a lot of data.
Yeah.
So we've been looking at a couple of options. I don't know if there are any like recommendations from you.
Well, so I mean, what we would usually do is just use Scoop before that, because the data is already kind of at that point it creates a MapReduce job. It's all distributed across the cluster and be able to push that data into the final data store.
So you do all the temp table and do the full table load with.
Yeah, exactly. I mean, there's ways to do Scoop, it exports with a particular condition too. So, but you can always create a temporary table if that's what you want to do.
Have you tried the Spark as an option to run all the data?
Yep.
Okay.
Yeah, we've utilized that as well. We've run into some execution memory issues, which you have to tune a little bit more than, say, Scoop. But that option does also exist as well. But Spark, I feel, is better utilized when you're actually doing some transformations because it's going to load the data into memory, and then, okay, it's going to dump the data out, but it's not going to do anything with it. But if you're going to transform the data, it certainly makes sense to do that in some way. But Scoop or Spark or some technology that runs on top of yarn is usually a better option.
I'm going to cut in here if you don't mind. Thank you very much to all our speakers, to Fred and to Robert and to Jacob for talking about these, about Jupyter and about Airflow. I think they're going to be around for a little bit longer if you have any questions, but we need to start wrapping it up so that we let everyone go home. So thank you very much, and we hope to see you next time.